I invite to this stage representatives of Hexagon Russia, Mikhail Petukhov, Alexander Kirichenko from Panorama, Anna Alibayeva from Director of Engineering Center, Anjun Hu Cha from photoman specialist from Grosko, Republic of Korea. We are going to give the floor now to Mr. Mikhail Petukhov, head of the Geospatial Department of Hexagon Geosystems Russia. And it is with great pleasure we're going to listen to the new features offered by geosensor Leica CityMapper-2. Hello, dear colleagues. It gives me pleasure to be here after a 6-year break, but we come to the conference only when there are things for us to tell you. Unfortunately, it doesn't happen every year. So the 3D mapping now. The term smart city and technologies appeared because of the situation which is happening with large cities now. There is information that soon 60% of all population is going to live in cities. Now, if we look at the daily migration, like for instance, every day about 1 million plus people visit Moscow, which creates a huge pressure on the urban infrastructure of Moscow, and management becomes very complicated, and the price of an error when making some managerial decisions grows up exponentially. In terms of the information object, the city infrastructure, or rather requirements for city infrastructure, requires information. So what kind of data we would need? Of course, 3D data, like buildings and so on. This data must be of high resolution. At the moment, our requirement is to create a system which would make data models based on 2.5 centimeter resolution. And the third thing would be the revisit, or rather updating of the data. Sometimes they ask us for twice a year, even 3 times a year. This is how often the information changes about the cities, so this is the kind of new requirements we have for geoinformation systems. In what way Hexagon can be held responsible or is trying to develop its systems to meet these requirements? I guess it was as early as in 2011, 2012, we received a request from a large city who wanted to build their detailed 3D model of the city with the update rate of twice a year. As a result of these terms of reference, we gave birth to our CD Penta Oblique system, which was released in 2013. If I'm not mistaken, that system was a sensor which included 5 cameras. 1 camera is nadir, and 4 cameras are doing oblique imaging. Then these data were processed. Based on 3D images, we built a highly detailed DM, and then we have restored vectorized building models, and we attached textures from the oblique images. It proved to be quite a successful system, which exists in Russia as well. Last year, that system captured New Moscow for 3D, quite a successful project at that. But we realized that the use of only images is not enough to achieve high level of automation. That's why the next version for us was the new hybrid sensor, which consisted of a laser scanner as well. So in the same box, we had 5 cameras plus a laser scanner. It was CityMapper system, released in 2016. It sold very well on the market. One company bought 30 such systems for their mapping applications, and this year at Intergeo in September, we released a new version of CityMapper called CityMapper-2, and this whole presentation is going to be about this new sensor, as well as some of its aspects that allowed us to improve the level of automation. of the 3D mapping application. First of all, CityMapper-2 uses our new cameras. This camera is specifically designed for photogrammetric application and photogrammetric quality. And next, I will explain why it is so. The camera is called MFC 150. MFC, it's multifunctional camera. The name is self-evident, and first of all, we use in this camera a sensor from Sony, 150 megapixel sensor. We believe that this is the best sensor available on the market at the moment. The same sensor is used by our colleagues from Phase 1, but that would be the end of any similarities here. Next, we've been thinking for a long time and analyzing how to use the ready-to-use optics for this camera, but eventually we came to a conclusion that we need to develop our own optics. In fact, this is the positionary concept of Leica and other imaging system producers, that optics need to be developed for a specific sensor to ensure the characteristics which would allow it to work with the sensor both in terms of resolution and the size of the sensor. By developing the proper optics, we can achieve a result when throughout the whole field of the sensor we have same resolution without any loss in quality, even if the sensor is large, has large dimensions. The next thing, we apply mechanical forward motion compensation in this camera. Because it's a CMOS sensor, that's impossible to do any electronic motion compensation. The only way to do it is the mechanical forward motion compensation. There is yet another method. We can shoot at a shorter shutter speed by reducing the blur, but we believe that forward motion compensation allows us to work with longer shutter speeds, which can ensure good quality imaging even with bad sun angles and low light conditions. And no matter how short the shutter speed is, still there is a blur in the image. Even if you don't see it, there is one, and it can affect the geometry as a result. Next thing, why is this camera photogrammetric? This camera was developed in such a way so that when we're changing the conditions of the work or operation, like for instance on the land surface we have 20 to 30 degrees. When we rise up in the air, it's minus 40. Under such differences in temperature, the camera must maintain its calibration parameters so it doesn't need to be recalibrated. So the optics was developed specifically to maintain under such difficult external environmental conditions, to maintain its calibration parameters. Next thing, considering the different imaging conditions, there are cities like Moscow with the restrictions on the altitude of imaging. We have developed a whole range of lenses with different focal length, also for the high precision and high resolution images for such cities with the altitude limitations. As a result, we came up with a camera which has the best image quality possible. It's a photogrammetric system, and it's a system that can be used for aerial photography without recalibration needs. These are some of the examples of these images. This is a 2.5 centimeter resolution, 48 degrees sun angle. You see that the details in the shadow areas are quite good. 20 degrees sun angle, but still in shadow areas you can see everything. One can easily decipher or interpret these objects. Here we see the oblique images. This is what the camera looks like in reality. This is quite a small camera. It weighs a few kilos. And you can see that the optics were developed by Swiss Optic. A few words about our previous system. It was CityMapper-1, or first generation. At the moment it is the highly productive system in terms of 3D mapping, because simultaneously it consists of 2 sensors, laser scanner plus 5 cameras in the same body. In a single flight we get both the point of clouds and a cloud of points and oblique images and nadir images, and so far we see no real competition on the market against this device. But still, we are releasing to the market this next version, CityMapper-2. It consists of 6 cameras now, because there are 2 nadir images. One is RGB, and the second one is near infrared band, because it's unfortunately impossible to do in a single sensor. 4 oblique cameras and laser scanner, which are all located, mounted on the same body. The main idea of building this sensor, and a technical terms of reference, was the sensor to ensure 2.5 centimeter resolution. This is what our system looks like. An important thing is that all the onboard infrastructure is the same. The platform, the operators, and the pilot monitors are the same. You can install DMC camera here and would work as well, because all the onboard infrastructure is highly unified, is highly homogenized. This diagram shows in what modes we can do imaging. An important thing here is that by doing the flights with 70% overlaps, and especially for city imaging, it's better to have 80% overlaps to exclude any blind spots. We can fly at the lowest possible speeds on the aircraft and do high-quality imaging like that. This slide shows the increase in productivity. The gray color shows the CityMapper-1 and 2 options with different focal length for CityMapper-2. And we have considerable increase in the coverage because of the broader capture. Also, we changed the configuration of the obliqueness of sensors. The oblique cameras have been turned by 90 degrees, which improves the triangulation capacities of oblique images because of the higher overlap and more connecting dots. Also, electronic capacities, onboard electronic capacities, have been increased. We're trying to make sure that at least part of the procedures and processing are moved into the sensor to save time on land. For instance, when CityMapper-2 does the imaging, we prepare overview of each image that can be memorized separately on the memory stick. And when you fly over, and for Russian conditions, this is the memory stick which is used for control overviews, and it's all done in flight. And this way we save a lot of time. This is what CityMapper looks like. An important thing here is that the system of storage is not a separate block, but rather a system embedded into the main system. Also, inside the system we minimized all the wiring, because there are only 2 monitors connected to it, and the power line, which increases its reliability. Also, CityMapper-2 uses our new scanner, Hyperion 2, which, compared to the previous scanner, has more robust characteristics, like the altitude of the flight is more than 5,000 meters. There is such a possibility, and we have a specialized system which allows us to simultaneously in air have up to 35 different impulses, which increases the density of the point clouds. And we use edge computing or peripheral computing. The scanner specifies the time of incoming impulses on the reflected signal, which increases the precision and reliability. At the same time, there is a possibility to store the digitized signal, and each reflected pulse is digitized, and based on digital signal, we identify the time of incoming and the altitude of that point. Equally important is that there is electrical scanning. In fact, this is like oblique ray, and there are many points of reflection on vertical surfaces also, which is very good for cityscape. We receive information from the facades of buildings.
This is a point cloud generated by such camera mode. High-performance sensor should come equipped with proper software so that it never becomes a constraint. We utilize software called HXMap, which we use for post-processing of sensor images or laser scanning. This is a unified system where the data load differs. All the rest is the same, unified, so we save money of our contractors, of our clients on training. I mean, whenever there is a new sensor coming out, there is no need to provide training on that because the software hasn't changed a bit. Apart from processing raw data, taking off a sensor, it is also possible to integrate in HXMap, orthophoto, if it's zero triangulation, and a special software product which helps build spatial models of city territories. This is how the interface looks like for HXMap. I think this is Bordeaux, France, showing the strips of laser scanning. As we process the laser point cloud or highly dense model off of the stereo pair, we define and generate buildings, roofs of the buildings. This has been done automatically. The technology is pretty smart. It starts with using points if there is deficient data. High density model is generated to make adjustments. Buildings are color coded. Green indicates high level of confidence. Yellow are those with question marks, not very reliable. No automatic mode will ever deliver 100% result in terms of reliability, so it's always possible to make adjustments. So if necessary, we can do superimposition. For example, here you can see that the roof of the building is misplaced, so we can make a correction. Next step is to generate textures off of oblique images. You can see what it results in. This building now has textures. Of course, there are blind areas like this one here, simply because we had nowhere to get texture from. So it gives you a texturized model. It's not a 3D mesh. Each building represents a separate object, We can assign any attributes to it, and if need be, we can delete this building from the model. So we attain a pretty good level of automation. Had we been tasked to do it manually, down the line we would have a pretty expensive product with no commercial prospect to hit the market. With this kind of approach, the data can be disseminated broadly on the market. In particular, an American partner who purchased 30 such systems generates such vector models, but the final product is, well, let's say you need to fix roofs, you can place your order, and this service will issue you with a layout, a blueprint of your building, and you will start doing what you need to fix instead of having an individual climb the ropes, getting onto the roof and doing a visual survey. Besides our contents program, which features orthophoto and GTMs, the next feature coming is 3D modeling. That's all I have. Any questions? What is the name of your software? Maybe I missed it. It's part of HXMap? Yeah. We used to call it 3D-Con, a German company that Hexagon purchased. They had the software that was marketed as 3D-Com. Mr. Sechin, Rakurs. Who needs those models? In other words, what's the main user group for those? You said that you had one service. So that company sells the data via cloud at a reasonable price, makes enough money to maintain 30 aircraft, have 11 offices, simply by selling rooftop layouts. Second application is in insurance. Estimating damages following natural disasters. So what they do is side-by-side comparison before and after the fact. Speaking of municipalities, they simply require 3D data to manage their cities better. So the data is really in demand. Hexagon was launched a content program in 2014 where we do aerial survey of the US, Europe, and put it on cloud, and then we sell access rights. Since 2014 this has been going on. We are resurveying the territory of the United States as we speak, and we will continue to add new products to it. The second product was the digital terrain model, which is what we collect, put on the cloud, and sell access to. It's just providing access to data. Users are wide-ranging, and the next step will be 3D data, where anybody and everybody can pay affordable amount to have access to it. Unfortunately, we don't have any time for questions now. Perhaps we'll